Let's look again at a velocity time graph. In this case, our velocity is not going to be 0 initially. Our initial velocity will be written as v sub I. Our final velocity at time is t will be v sub f. So we can do the same thing we did before and write an equation for this line. If y equals mx plus b, we can make our substitutions so that the y represents the value on the y-axis. So in this case, it could be our final velocity. If the slope is the acceleration, the time is on the horizontal axis, and our y-intercept this time is not 0, but it is some non-zero initial velocity. Now this is convenient because in many cases, the initial velocity is not 0. However, most times you won't see the equation written in exactly this form. We usually see it written as v final is equal to v initial plus at. This is just like the equation we wrote when there was an initial velocity of 0, but this time we want to make sure that we understand and we recognize that when our initial velocity is not 0, we need to account for it. We can solve a problem like this one. A car is moving at 25 meters per second and speeds up to 30 meters per second in 2 seconds. What is the acceleration of the car? You can always sketch out the graph. It's very helpful. So this shows me that initially my velocity is 25, later my velocity is 30, and it takes a 2-second time interval for this to occur. So what's the slope of that line? Remember, the slope is the acceleration. Well, knowing our final velocity, our initial velocity, and our time, we can either use the slope equation, or we could use this equation that we get from the equation of the same line on a velocity time graph. So v final equals v initial plus at. Now I want to substitute. So my final velocity speeds up to 30 meters per second. So that is my final. My initial is moving at 25. So that is the initial velocity. Plus, I don't know the acceleration, so I'll leave an a here. And then the time for this change was given as 2 seconds. Do our algebra. 30 minus 25 would be 2a. 5 is equal to 2a. 5 divided by 2 is a. So the acceleration is 2.5 meters per second squared. So now the question is, what was the displacement of the car? If you recall, displacement is the area under the graph. But this graph does not have a 0 initial velocity. So if we look at the graph, when you have an initial velocity that is not 0, and we've got some final velocity and some time, we would need to find the area under this line, and that area would represent our displacement. Now, that is not an easy object to do, so we could think about splitting this into a rectangle and a triangle, just to make the math a little easier. So this bottom part is the easiest, so I'm going to start with it. So the area of this rectangle down here is base times height. So the base, t, times the height, v initial. So that takes care of the area of that piece there. Now let's do this piece here that's a triangle. Now a triangle's area is 1/2 base t times height, and this is the height from the initial velocity to the final velocity. So that height would be the final velocity minus the initial velocity. So now we want to put these two together to get the total area. So if I have the area of the rectangle plus the area of the triangle, I'll have the area of the whole shape. So I get that the change in position is equal to time times the initial velocity plus 1/2 time times the final velocity minus the initial velocity. Now, in a lot of cases, remembering a subtraction step in an equation is very difficult. But I remember that the slope of the line has a change in, there's a rise over a run. So I'm going to make a substitution here. So if acceleration is the final velocity minus the initial velocity over the final time minus the initial time, then that would mean that if I multiply both sides by time, the acceleration times time would be equal to the final velocity minus the initial velocity. So now I'm going to substitute a times t in here for this change in velocity. So then we would have that the change in position is equal to time times v initial plus 1/2 time times a times t. Because remember, we're taking this and substituting it in for the parentheses. Now, when I look at this, I also see that there's a time and a time here. So if I multiply this time, t, in here, I'll have 1/2 a t squared. So I want to put the t squared at the end because it has the exponent there. Plus, and typically you'll see these two terms written in the opposite order and have v initial times t, which doesn't change anything at all. It's just a way it's always been written. So if you look it up in a book or anywhere else, that's what you'll see. So this is a general equation that will allow us to determine the change in position or the displacement of an object with a non-zero initial velocity. So let's go back to our question. What was the displacement of the car? So we know that the initial velocity was 25 meters per second. The final velocity is 30 meters per second. We have a time and we found the acceleration. So now we can use our new function for determining the displacement of our car. So let's look at that. So this is the function that we're going to use. So let's do our substitution now. Our change in position is equal to our initial velocity, which was 25, times the time, which is 2 seconds, plus 1/2 the acceleration that we just found, which was 2.5 meters per second squared, times our time, 2 seconds, and then squared. So doing our calculation here, 25 times 2 would be 50, plus 1/2 of 2.5 times 2 squared should give us 5. That means that our change in position would be 55 meters. Again, the important steps to show when showing your work for me would be for you to write the equation you're going to use down, show your substitution, and then your final answer. Now let's consider another case where the initial velocity is actually greater than the final velocity. From before, we have discovered or determined that the acceleration is the slope of the line, and this slope is negative. So we have a negative acceleration, and the velocities are all on the positive side of our graph, so the velocities are positive. When you have a positive velocity but a negative acceleration, you get a situation where there is slowing down. So in this case, our object is slowing down. It has a high initial velocity and a low final velocity. Now I can still use my equation that I developed earlier, that v final is equal to v initial plus at. So let's give this some numbers. Let's say that our initial velocity is 20 meters per second, and our final velocity is 5 meters per second. And the time is 10 seconds. And we want to find what is the acceleration. So I could use these numbers and determine the slope of the line, but that's the same as using this pre-made equation that we developed earlier. So using the equation, I would substitute my final velocity of 5, my initial velocity of 20, a is unknown, but time is 10 seconds. So doing our algebra, 5 minus 20 is equal to 10a. So negative 15 divided by 10 on both sides gives me the acceleration. So in this case, my acceleration would be negative 1.5 meters per second squared. So that tells me that for every second, this object's velocity is decreasing because it's moving in the positive direction, but we're adding a negative to it every time. So it's decreasing, and at the end of the time interval, the end of the 10 seconds, it has slowed to a velocity of 5 meters per second. But the object is still moving in the positive direction because the velocity is still positive at this point. Let's look at another case where our initial velocity is 2 meters per second, but our final velocity is negative 6 meters per second. And the object has this negative 6 meters per second velocity at 4 seconds. So just to show a graph of the motion, we would have a line like that. Now that negative slope tells me the acceleration will be negative. Now if you remember, at this moment right here, the velocity is 0. So our object has stopped momentarily and has gone from moving in the positive direction to moving in the negative direction. So in terms of a car, maybe the car is slowing down, it stops, put it in reverse, and then hit the gas pedal and back up and speed up as you're backing up. It's like the Fast and the Furious. So in this case, I can still use the slope form to find the acceleration, or I can think of this as one of my v final equals v initial plus at. So my final velocity is negative 6. My initial velocity was 2. The acceleration I don't know, and it takes 4 seconds for this to occur. So then my algebra step, negative 6 minus 2 on both sides gives us 4a. So negative 8 divided by 4 on both sides gives me a. So then the acceleration is negative 2 meters per second squared.